Right, good afternoon. Welcome back to Advanced Modeling Methods. And today's lecture 5, and we'll continue our formulation of the method of weighted residuals. And so far, we've looked at the method of weighted residuals from the point of view of global collocation of polynomials. Then we looked at local collocation of polynomials. That's what we did last class. And that resulted exactly in the same form as the finite differencing method. So exactly as if you were to take the differential equation and approximate the derivatives using finite differencing, and then you end up with the same algebraic form as finite differencing. So now we basically demonstrated that from the method of weighted residuals, we can get to the finite differencing method. Now let's look at another class of method of weighted residuals, and this is advanced modeling methods, and we're up to lecture 5, and we're going to look today at the subdomain method of weighted residual. And you see the trend here. Basically, we change the weight functions to something different. We call it a different method, and it would lead to another technique, which is commonly known or popularly used in commercial codes. You'll see what this one will lead to. So in this case, the domain omega is subdivided into n subdomains. Omega I going from 1 through n. So basically, if we're looking at a 2D problem, and this will be the domain, somehow this will be the entire domain omega, and this is, let's say, x and y, this is a 2D domain. Every one of these little pieces is a subdomain, such that the domain is basically the summation from I equal 1 to n of all the subdomains. Now that doesn't say anything about the weight functions, and remember that we basically classify the different methods of weighted residuals based on the type of weight function we use in the minimization of the residual. So in this case, the selection of these subdomains will serve the purpose of selecting the weight functions. The weight functions are selected such that the weight function omega I, the ith weight function, is equal to 1 if x belongs to the subdomain and 0 if x doesn't belong to that subdomain. So basically, the weight function is 1. However, it vanishes outside that subregion. So essentially, we're looking at this. Remember that for interior methods, which are basically the ones that we're concentrating on, we had the summation, the integral over the domain of the residual, whatever, the domain residual, which is basically the governing equation, the approximation of the governing equation, times the weight functions is equal to 0. Since the weight functions are simply 1 or 0, this will basically mean that this will translate into the integral over the ith subdomain of the residual, such that I goes from 1 to n. That's it. So the method will just simply reduce to this. But we have to carry out the integral. Now in previous collocation techniques, the weight function was the Dirac delta function, and therefore the integral disappeared. The integral went away. Now the integral stays, and we have to deal with it. In 1D, it's easy to deal with an integral, especially if the residual is made up of an approximation that includes polynomials or whatever. We can always integrate polynomials with no problems. But when you go to 2D or 3D, then you need to worry about how are you going to conduct these integrals, and that's why you introduce shape functions that are integrable and so on. So let's see. So to implement this, let's look at the 1D example at hand. So we have this example that we've been working with, where the governing equation, again, I'm going to recast it, says that the second derivative of the temperature plus the temperature plus x is equal to 0, such that x belongs to the interval from 0 to L. So it's a 1D problem. And we have first kind boundary conditions, which always make things very easy, or easier. So that the temperature at 0 is equal to some T0, and the temperature at L is equal to some TL. So introduce an approximation, same thing. Same thing that we've done before, either of this kind, j equal 1 to n of alpha j, phi j with respect to x, or, say in parentheses, locally supported. It can be global like this throughout the entire span of x, or it can be locally supported within a space. In either case, it's just an approximation, such that exactly satisfy boundary conditions and approximates the governing equation through a residual. So in this case, the residual within the domain is just this. Okay, so these function, this approximation is set in such a way that exactly satisfies this, and that it approximately satisfies the governing equation, so it's not quite equal to 0, but it's almost equal to 0, is a residual. So nothing different from what we've been doing so far. Minimize through. So we minimize the residual by requiring that in an integral fashion, this goes to 0. This is the domain. Now we know that the domain is a 1D line that goes from 0 to L, and that because we're going to be using subdomain method of weight residuals, this turns out to just be 1. All right, so using subdomain method of weighted residuals leads to, well, this will be the integral from every subdomain the residual being the second derivative of t plus t plus x times 1. All right, so in a 1D problem, it's very easy to set up the subdomains, right? We just set up some nodes, n number of nodes to be exact, along the entire domain, and then break up the problem. So the subdomains will look like this. So we have, let's say, x1, xn, as many nodes as we decide to break up the domain with. This is xi, this is xi plus 1, and this is xi minus 1. So our domain will be the region around node xi, halfway through the next node and halfway through the previous node. So this is the domain. Omega I, which as you can see is of size delta x. So basically it goes from x I minus a half to x I plus a half. And it is of size delta x. By the way, at node xi minus 1, we have the discrete temperature Ti minus 1. At node xi, we have discrete temperature Ti, and so on and so forth. Same thing we did last class. However, in last class, all we did was just locally approximate, use 3 nodes to throw in a parabola, right? That locally approximated the temperature distribution using that parabola through the 3 nodes, and we use the same direct delta functions as weight functions, so that led to collocation, and local collocation led to finite differencing. Right now it's going to be slightly different because we still have to deal with the integral. The integral didn't disappear, which is usually a good thing for numerical techniques, that an integral stays. Because when you try to solve something in strong form, this is called strong form. An equation, a differential equation, is called the strong form of the conservation. You're basically doing a point-wise conservation of equilibrium, or maintenance of equilibrium, point-wise, when you do this, the strong form. So you're basically satisfying the differential equation point by point, but it says nothing about the global equilibrium of whatever phenomena is behind this. If you're talking about heat conduction, this came from energy equilibrium. This came from the first law of thermal. That equation came from the first law of thermal. Energy goes in, energy needs to go out, right? Energy can be stored. In this case, it's not stored because there's no time derivative anywhere. And energy can be generated, and this could be the generation term, okay? And any any energy balance or momentum balance or whatever quantity balance comes from an integral type of equilibrium. The fact that the integral stays, it means that you are somehow enforcing global equilibrium. At least piecewise, you're connecting all these pieces, but you're enforcing inherently the global equilibrium. So not only you'll find a solution using this, not only you'll find a solution that will minimize our residual point-wise, but at the same time, it will somehow enforce the global equilibrium of that system. Okay, so these techniques are usually better in terms of global equilibrium than collocation techniques. Collocation techniques might be more accurate and easier to implement, but techniques where the integral stays tend to be better from the point of view of equilibrium and also from the point of view of stability. All right. So what this will reduce to is then the integral between x I minus a half to x I plus a half of the second derivative of the temperature approximation plus the temperature approximation plus x dx must be equal to 0. And now we can only do this from 2 to n minus 1. We cannot do it at node number 1 because the field space to the left of node minus 1 doesn't exist. Okay? This will be node 1 minus a half, which doesn't exist. That space is not part of the domain. All right? So we have to come up with something else here, and we have to come up with something else right here. So this will give us n minus 2 equations. But we have n temperatures to worry about, n temperatures to determine. All right. Now what do? I'm going to break that up. I'm going to break that up into 3 integrals. One is going to be the other one is going to be and the other one is going to be all right. And what I'm going to do, so if you look at this integral, this is the integral of the second derivative of dx. What is the integral of the derivative of something? Just something, right? So the integral is an antiderivative. So basically, the integral of the derivative of the derivative of the temperature is the derivative of the temperature. Clear? So it would just be dt dx. Evaluated at the 2 limits of integration. All right. So I'm going to keep writing this. So I've done this in one step, but I want to go step by step, and I'm going to just basically say that this is dt dx evaluated at x at I plus a half minus dt dx evaluated at x at I minus a half plus all right. So what do we do now? We need to worry about these two quantities, which are the derivative of the temperature evaluated at the interfaces. The two interfaces is the subdomain. Those are called the interface fluxes. Well, these are related to the fluxes. Remember the flux Q is minus K times the T dx. Okay? So this is definitely related to the fluxes through K. So fluxes at interfaces. To the left and to the right and to the left. So to evaluate the interface fluxes and the temperature integral, we must introduce a local approximation for the temperature. P of x. And the obvious choice, again, because we have three nodes, if we go back to what the interface is, we basically have the subdomain. We have one node inside the subdomain, and then we have two nodes adjacent to the subdomain. So the obvious choice is to use, again, a parabola because we have three nodes. Okay, three nodes will give you exactly a parabola. Let's use a second order polynomial with local support on xi minus 1, xi plus 1. So in that range. So basically, let t of x be equal to a plus b, x minus xi. Same thing we did last time. Such that x belongs to the interval between xi minus 1 to xi plus 1. To find a, b, c, enforce that t at xi minus 1 must be equal to ti minus 1. T at xi must be equal to ti. T at xi plus 1 must be equal to ti plus 1. The usual, right? So we selected a parabola because a parabola has three coefficients. And since we have three nodes, we can generate three equations. Three equations to find three coefficients. This results Ti plus Ti plus 1 minus Ti minus 1 over 2 delta x times x minus xi plus Ti plus 1 minus 2 Ti plus Ti minus 1 divided by 2 delta x squared times x minus xi squared. So that's a local approximation. Exact same thing as we used before. But it's not going to result in the same formula and in the same algorithm, because before the wave function was the director of the function that led to collocation, and this time the wave function is just one, so that the The integral doesn't disappear. All right. So now, this is the formula we have right here, and I'm going to encase this. On the previous page. These are called the fluxes at the interface. I'm going to call this, I don't know, integral 1, and I'm going to call this integral 2. I'm going to be solving them one by one. Well, the last one doesn't need a temperature approximation. We can do that right away. Okay? But let's see. Now that we have the temperature, we can calculate the fluxes, right? All we need to do is differentiate this. Right, so where dt dx is equal to what? Would be ti plus 1 minus di minus 1 divided by 2 delta x's. And this 2 and this 2 will disappear, plus ti plus 1 minus 2 ti plus ti minus 1 divided by delta x squared times x minus xi. So with that, we can calculate the fluxes. Flux to the right, flux to the left. So, therefore, let's fit it here, dt dx at xi plus a half, for example, is equal to, well, this will stay. And this will be ti plus 1 minus 2 ti plus ti minus 1 over delta x squared times xi plus a half minus xi. What is xi plus a half minus xi? What is the distance between the right of the node halfway through the subdomain to the node? That's half of delta x, right? This is delta x over 2. So these will basically be ti plus 1 minus ti divided by delta x. So the derivative of the temperature at the right interface is, no surprise, the temperature of the right node minus the temperature of the center node divided by the distance in between. It's a first order approximation of the derivative. It's just like a finite differencing approximation. And likewise, when we do dt dx xi minus a half this will be xi minus a half minus xi, which is, how much is that distance?
Still delta x half.
Negative, right? Negative of that. This coordinate minus this coordinate give you a negative number minus delta x over 2. So that equates to ti minus ti minus 1 over delta x. No surprise again, the derivative of the temperature halfway between the center and the left is basically the temperature of the center minus the temperature of the left divided by the distance between them. It's a first order approximation of the first derivative. All right, so we have the fluxes. So now we need integral 1 and integral 2. We need that integral of the temperature on the subdomain. So that would be integral 1 is equal to the integral between I minus a half and I plus a half of the temperature dx. So therefore, I1 is the integral between x I minus a half, x I plus a half of, maybe we should do brackets, Ti plus Ti plus 1 minus Ti minus 1 over 2 delta x times x minus xi plus Ti plus 1 minus 2 Ti plus Ti minus 1 over 2 delta x square x minus xi square dx. All right, so I1 is equal to, well, the temperature of Ti, integral of Ti is Tix, evaluated between xi minus a half, xi plus a half, plus the integral of these, this is a constant, would be x minus xi squared over 2, again evaluated between minus a half and a half. And the last one is all a constant. X minus xi cubed divided by 3, again evaluated between xi minus a half and xi plus a half. All right. So what is this going to be? It's x, it's Ti times x evaluated here, minus Ti times x evaluated here. So that's Ti times delta x. Because this one minus this one is delta x, right? This one is this times x minus xi squared over 2. Well, x minus xi evaluated here is delta x over 2, positive, right? Because when we square it, it will be delta x squared over 4, positive. And this one is minus delta x over 2. When we square it, it will be positive delta x squared over 4. So that one will cancel out, okay? And this one stays because the cube of a negative power is cube. So I1 will be Ti delta x plus 0 plus this will be Ti plus 1 minus T minus 2 Ti plus Ti minus 1, and this will be delta x divided by 24. So when we combine this, we get I1 is equal to delta x divided by 24 times Ti minus 1 plus 11 delta x over 12 Ti plus delta x divided by 24 ti plus 1. Okay. Now I2 is equal to the integral from x minus a half, xi minus a half to xi plus a half of x dx. That one's simple because this will be x squared over 2 xi minus a half xi plus a half. So that would be xi plus a half squared minus xi minus a half squared divided by 2. So I2 will be I can do the binomial square, and that would be xi plus a half plus xi minus a half, leave the 2 here, times xi plus a half minus xi minus a half. Right? So, what is this? Delta x, right? And this, halfway, the right interface and the left interface, it's just xi, right? So, I2 is equal to xi times delta x. Now we have all the components that go into the residual minimization. So plug these back into residual minimization. So we have the fluxes. One is Ti plus 1 minus Ti divided by delta x. The other one is Ti minus Ti minus 1 divided by delta x. Integral 1 resulted in delta x over 24 Ti minus 1 plus 11 delta x divided by 12 Ti plus delta x divided by 24 Ti plus 1, and I2 resulted in xi times delta x, and this is equal to 0. All right, so I'm going to combine this. And divide by delta x. So this would be Ti plus 1 minus 2Ti plus Ti minus 1 divided by delta x squared. plus 1/24 of ti minus 1 plus 11/12 of ti plus 1/24 of ti plus 1 is equal to minus xi. I've divided everything by delta x and pushed the xi to the right because that is the forcing function. And I don't know if you remember what we did last class, we had collocation with local support, which resulted in finite differencing. And in finite differencing, remember the equation that we're trying to solve has the second t dx squared, the second derivative of the temperature. It has the temperature, and it has x, right? When we do local collocation, we end up with a finite differencing approximation of the second derivative, which is now identical. See, we ended up with the same approximation by doing the integration. We end up with the same exact approximation, but t at node I is no longer just t at node I. That temperature, when integrated, has portions of the temperature to the left and portions of the temperature to the right. Small portion though. It's 1/24 of it and 1/24 of this one. And this is what the integration does. This little thing here is the only difference between finite differencing and what we got, which is finite volumes. Okay? So this is exactly equivalent. So when we combine this, we have 1 over delta x squared plus 1/24 of ti minus 1 plus 11/12 minus 2 delta x over 2 ti plus 1 over delta x squared plus 1 over 24 ti plus 1 is equal to minus xi. This is this algebraic form of the subdomain method of weighted residual is perfectly equivalent to the finite volume method, FBM. Not to be confused with the finite element method, that's something else. This is a finite volume method. It is a very common technique. It is as common as a finite element method. You use finite element every time you use CATIA and do structural analysis, or every time you use ANSYS and do some structural analysis. The technique of choice for structural analysis, solid mechanics, is FEM. But every time you do CFD, under the hood of the code that you're using is a finite volume solver. Okay? It's something, whether you use Fluent or CFX or Stars and CM, whichever one of those solvers you elect to use for computational fluid dynamics, the technique of choice is finite volume methods. FBM is the technique of choice for computational fluid dynamics, a little better known as CFD. So CFD codes do not use FEM. They don't use finite elements, they use finite volumes. Completely different. We'll see next week how finite elements come about. But finite volume is just simply a piecewise conservation of the integral conservation of the governing equations. And as you can see, the only thing that differs, or in this formulation, the only difference between these and finite differencing, this is identical, it's just this. That it's not just t evaluated at I, it changes a little bit, the algebraic form, because of that. Okay. So in this case, well, this is equivalent, this is valid in this range. We cannot apply it at I equal 1. Why not? Because this will point to t0, which doesn't exist. We cannot apply it at I equal n, because this will point to tn plus 1, which doesn't exist. This is outside the domain. So this only generates n minus 2 equations, and we have n temperatures to worry about. The other two we get from the boundary conditions. So the algorithm at I equal 1, xi equals x1, T1 is equal to T0. So that's the first entry in the matrix. See, these are simultaneous equations. You cannot solve for T2 without knowing T1 and T3. You cannot solve for T3 without knowing T2 and T4, and so on and so forth. So you have to solve them simultaneously. At I from 2 to n minus 1, xi is x2 to x minus 1. We have this equation. 1 over delta x squared plus 1 over 24. Try to fit it here. 11, 12. 2 over delta x squared. 1 over delta x squared plus 1/24 is equal to minus xi. And at n, well, in this case, again, it's simple because we have a first kind boundary condition. Again, that makes things very simple. The nth temperature is just that impulse value TL. And now we have a square matrix, right? We have n minus 2 equations here. We have equation 1, equation n. That makes up n equations for n unknowns. Although the first and the last unknown are solved explicitly. So, okay. So what if, for example, in the first node, a flux is applied instead of a temperature? How will you deal with that? Having a temperature applied, the first kind boundary condition at the first node, makes this very simple, because we can get T1 as just an imposed condition. We need an extra equation that relates the temperature at 1 to something else. So, let's see. What if a second kind condition was applied at x equals 0? For example, that means that the Q, right, at x equals 0, which is defined as minus k dt dx times the normal vector at x equals 0, which is minus 1, x equals 0, is equal to some flux, Q0. We were told that there's a flux here on the left. At the left, the normal vector is minus 1. On the right, the normal vector is plus 1. Points to the right. The normal vector always points outside of the domain. Always. The definition of normal flux, the Q, is minus k dt dx. This is the flux vector. But at the boundary, has to be multiplied by the normal vector. Minus 1 on the left, plus 1 on the right. So this is outward drawn unit normal vector. All right, so that basically means that dt dx at x equals 0 is equal to Q0 over K. How do we impose that condition? How to impose? Well, we have two options. Option one, use finite differencing approximation of dt dx. So that is, this is node 1, and this is node 2, and here we have Q0 applied in there. The finite differencing approximation of T1, of the derivative, would be dt dx at x1 is equal to T2 minus T1 divided by x2 minus x1, which is simply T2 minus T1 divided by delta x. Therefore, T2 minus T1 divided by delta x is equal to the imposed value Q0. So the equation at I equal 1 will simply be minus 1 over delta x times T1 plus 1 over delta x times T2 is equal to Q0. So that will replace the first equation. That will replace this equation in the matrix. The one that says T1 is equal to T0 hat will be replaced by this one. It's another simultaneous equation. So that's option 1. Use the finite differencing approximation of dt dx at x equals 0. Option 2. Use residual minimization at omega 1, at the first subdomain, which is half size. Half size subdomain. So this would include basically saying the integral, and let me, before I draw the integral, this will be x1, this will be x2. And I can continue, x3. Remember, we have this Q0 imposed in here. So this is subdomain 1, this is subdomain 2, which is twice the size. So this would include basically saying that the integral from x1 to x1 plus a half of the second t dx squared plus t plus x dx is equal to 0. So we're applying the same formula, but we're applying over half the size. See, it doesn't go from x1 minus a half to x1 plus a half. So we're gonna do exactly the same, simply that this would be the second derivative, dt dx at x1 plus a half minus dt dx up here, dt dx is q0 over k. That's the condition, dt dx q0 over k. That's the equation that results. This is at x1 plus the integral from x1 to x1 plus a half of dx plus the integral from x1 to x1 plus a half of x dx is equal to 0. This one will result in T2 minus T1 divided by delta x. That's the flux at this interface is this temperature minus this temperature divided by this distance, which is delta x. This is from the approximation of the temperature, same thing we did before. This one is Q0 over K. That's the imposed value. That's the TDX right here. And plus this is this integral, which I'm going to explicitly write as the integral, plus whatever this is. This is going to end up being x1 times a half of delta x, and this one is going to relate delta x squared, temperature, first node and second node, and so on. Right? We don't have 3 nodes to do an interpolation, so we're going to use linear interpolation of t, which is basically x minus x1 divided by x2 minus x1, which is delta x, times t2 minus t1. And x is equal to x1. This is 0. And x is equal to x2. I get t2 plus t1. So we integrate that. These results in an equation of the form similar to the one we did last time. Some coefficient times t1 plus some coefficient times t2 is equal to some coefficient times q0. Plus maybe some additional coefficients. This is more accurate because it balances the energy. Okay? The previous option was just a finite differencing approximation. This one is a balance of energy. I am integrating the entire differential equation, so not only I am enforcing the flux, but I am balancing the energy on that first subdomain. All right. So that's what happens when you have a second kind condition. Makes things more complicated on the first node. Or if you have a second kind condition on this last node, you'll have to go through the same approach. All right. So let's go to the computer. This time I'm just going to show you the
Is the syllabus posted online somewhere?
on campus.
Okay, I couldn't find it, but I might not.
Under files.
Files.
Just
Okay.
go under files.
So I wanted to check the scheduling.
Yeah, I can show it to you now actually.
Because if we're finishing up this segment, I'm guessing we have that thing due soon.
Yeah. So semester, spring 16, and the calendar goes like this. So we're finishing the subdomain method. Next week we'll do Galerkin and least squares. And then next week, at the beginning of next week, I'll give you, you see the trend. Basically the homework will be a problem in 1D, where you would just solve it with these different techniques and turn in a report of what you get with respect to an exact solution that I'll give you. All right, and then it's due on this Thursday, 2/11. We don't have classes that day, so you can use that day to solve the problem. So I'll give you at least a week and a half for that. All right, so let's go to MathCAD. So we're essentially looking at the same problem, where the initial code solution, the exact solution is a cosine-sine combination, and the exact solution for this particular problem, where temperature on the left is 15, temperature on the right is 25, and the length is 1, looks like this. We're gonna start with the origin equal 1. We've done the same all along. N is equal to 11. Delta x is L divided by n minus 1, so the size of each subdomain is 0.1. And the location of each node xi, which is indexed by I, is I minus 1 times delta x. I initialize the matrix A, make sure every element of the matrix is 0 before I start, because the matrix is going to end up with a lot of 0 elements because it's a local technique, local support technique. So I make sure that there's no garbage on memory, so make everything 0. So the first equation says that I equal 1 because this is first kind boundary condition. The first element of the matrix is 1, and the first element of the right-hand side vector is T0. That means that temperature, the element 1, 1 of the matrix, which multiplies T1, is equal to T0. So the first nodal temperature is equal to the impulse value of TO. The other equations from I equal 2 to n minus 1, all the remaining rows except the last one, will have the diagonal term, I, or AII, is 11/12 minus 2 over delta x squared. The one to the left is 1/24 plus 1 over delta x squared, and the one to the right is 1/24 plus 1 over delta x squared. That's basically the algorithm that we ended up with. And the right-hand side vector is the forcing term. This equation has an x, so you end up with a minus xi on the right. And the last equation, the last row of the system, is the same as the first row. It's just that the last diagonal is 1, which multiplies Tn, Tn is equal to TL, that's the last equation. It's basically an explicit equation. We don't even need to have it in the system of equations, but just for completeness, we add it. So, this is a system that is 11 by 11. We solve it, we call it TFBM, the finite volume method. Temperatures is A to the minus 1 times B, and let's see how accurate those are. And again, because this doesn't provide us with a continuous temperature distribution, but instead of nodal representation of the temperatures, a discrete representation, what I'm going to do is plot it against, the exact solution, which is that red line. And instead of tracing the numerical solution, I'm just going to use symbols at the nodal locations. And as you can see, qualitatively, it looks good. And the error, 9.22 times 10 to the minus 3. If you open the lecture 4 slide, which uses local collocation, and compare it with the same type of discretization, this error is a little bit better. Not only that, it's a lot more stable. You can actually increase the number of nodes and you don't lose fidelity. So the round of the truncation error doesn't propagate as much. So you can make this number 101. Obviously a lot more nodes. And this error from 9.22, if I update it, will be 9.6 times 10 to the minus 5. This is an indication that the error is actually decreasing quadratically, right? Because I made the spacing a tenth of the size. So I increase the resolution of nodes by a factor of 10, and the error decreased by a factor of 100. So you have a quadratic model here. Okay, and that's it. Any questions? You can go as high as you want, and you won't start losing fidelity until you get to a very, very large value, but you can go to 1001. Notice the delta x is just 10 to the minus 3. It takes a lot longer to solve the system of equations, but not that much. And if you update this number, we should see 10 to the minus 7, or close to 10 to the minus 6 actually, this is 9.6. So there it is, 10 to the minus 7. So it's still quadratically reducing, so the round of error hasn't even shown up yet. All right. Questions? So next week we'll do Galerkin, method of weighted residuals, least squares, and that's it. You see the trend. There's basically all the different approaches, and nail down this to the ground, and be able to implement it, and then we'll move into more specific boundary element math. All right. So I'll see you next week.
Just a question on MathCAD in general. Is there a way to make it auto-update that value? Because I assume it doesn't update it because it doesn't use it for other things.
It is supposed to be auto-updated, but because there's so many things that it's calculating, it's just a flaw.
Okay.
Because I have to set it up for auto.
Could you put like at the end, right after that, like just display that value, and then would it update that? Because it's the last thing. It's only the last thing that doesn't update.
Yeah.
Right?
If you look here, there's an option here for update. My tools.
Yeah.
Calculate. There's a calculate, which is F9. This is what I use.
Okay.
And I have this set up for automatic calculation. It's just not for some reason. There's a flaw.
Yeah.
And I guess it's just a compatibility issue, but it doesn't completely automatic. It's supposed to be calculating everything on the background, but it's not.
Yeah, my guess was just because it's at the end, it's just not using that value, so it doesn't know that it needs to.
See, if you change something, see what I think this is a bug in the code. Let's say I change it back to 11. Everything is done properly except that number, so it doesn't update. But if you go and save, see what happens?
Yeah.
So it is definitely a bug. All right.
Some kind of optimization thing, maybe.
Yeah.